Hi there, welcome to Labster's Virtual Lab. Today we will learn about collisions and conservation of momentum. This simulation uses voiceovers. If you don't have audio, click the speaker symbol on the top right of your lab pad to switch the play mode. If you disable the sound effects, the lab pad will slide up whenever there are instructions to read. You can select what type of audio you prefer. Deselecting any of the options will mute that option. Click Continue to learn how to navigate through your mission. Using the lab pad is an important way to get the most out of this simulation. Is this the first time you are playing a Labster simulation? Perfect, then let's get started with your first mission. I think that a game of billiards will be perfect to study collisions. In fact, the best players not only know where the target ball is going but also where the cue ball will end up. Physics will help us understand how. Plus I had promised Newton I'd teach him how to play pool. Click on Newton to talk to him.
Hello friend, Dr. One offered to help me with pool, and I would be glad to count on you as well. I keep losing against my fellow Hook, and I can't accept such an embarrassing defeat, so I have resolved to study the matter scientifically.
Move to the pool table. The principles of the game are pretty straightforward. You have to send the balls into target areas by giving them a certain velocity. For a start, you could try to get the white ball in the target area. Click on the arrow next to the white ball and set up its speed to send it into the target zone. Press ready when you are all set and observe the values of the velocity and momentum of the white ball when the shot is taken.
Well done. Have you noticed that once the ball has been struck it keeps moving at a constant speed and on a straight line? This is because there is no net force acting on it. Anyway, I think you usually play pool with more than one ball. Am I right, Dr. One?
True, but don't worry, we'll use more than one ball. Try to make the yellow and white balls collide and get the yellow one in the target area. It's just a matter of giving the right velocity to the white ball. Also, see if you can spot which quantities don't change during the collision. Click on the arrow next to the white ball and get the yellow ball into the target zone. Press ready when you are all set and observe the values of the velocities and momenta of the two balls when the shot is taken.
That's very curious. Before the collision, the white ball was moving, while the yellow one was at rest on the table. After the collision, it's like they exchanged velocities. In physics, we often try to find things that remain constant. We call these conserved quantities. Was there anything that was unchanged during the collision we just observed? That's right. The sum of the velocities of the two balls remained constant even though the velocity of each ball changed. Let's see if this property is valid also in other circumstances. We could experiment with balls made of different materials. I want to try with a ball of soft clay. It is about as heavy as a pool ball. Let's see what happens when we hit it with the white ball.
Click on the arrow next to the white ball and get the soft clay ball into the target zone. Press ready when you are all set and observe the values of the velocities and momenta of the two balls when the shot is taken.
Hey, did you see that? What happened in the collision between the white ball and the clay ball? Exactly. Even if we change materials and velocities, we find that the sum of the velocities of the two balls always remains the same before and after the collision.
Although the sum of velocities was a conserved quantity in both of the collisions we have observed, the motion of the balls was pretty different. This is because the first collision we observed was an elastic collision, while the second was inelastic. We call a collision elastic when kinetic energy is a conserved quantity of the collision, and inelastic when it isn't. In inelastic collisions, some of the kinetic energy is spent to produce some other effects during the collision, like heating the balls or denting them.
Very well. Does that mean that kinetic energy is also useful in pool?
The answer is, not always. Conserved quantities are very useful in pool. They help you predict the direction and velocity of the cue ball. But, as we have just seen, kinetic energy isn't always a conserved quantity.
I see, the kinetic energy is useful just when we deal with elastic collisions, in which the kinetic energy is also conserved. Now I want to experiment with balls of different masses and see what is conserved.
Good. Then, let's use the purple ball, which has 3 times the mass of the white ball, and make them collide. Click on the arrow next to the white ball and get the purple ball into the target zone. Press ready when you are all set and observe the values of the velocities and momenta of the two balls when the shot is taken. What a shot! What are the conserved quantities in this collision? That's right. What is conserved in collisions is the sum of the momentum of each ball. We call this sum the total momentum of the two-ball system. If there are no external forces on a system, then its total momentum is conserved.
We have learned that conserved quantities are very helpful in a game of pool. We also saw that the kinetic energy is not always conserved in collisions, and this begs my next question. Do you think total momentum is conserved in all kind of collisions? Exactly. Momentum is always conserved during a collision, even if that collision is inelastic.
Would you like to learn more about momentum? Perfect. Let's go on helping Newton with pool then. Remember, you can check out the theory tab on your lab pad at any time to learn more about momentum. Before we go on, would you like to learn more about elastic and inelastic collisions, energy conservation, and momentum conservation? You can check out the theory tab on your lab pad at any time to learn more about elastic and inelastic collisions and energy conservation.
Dr. 1, do you think all this information is enough to help me get better at pool?
Absolutely. You are now able to determine how the cue ball will interact with the other balls. In fact, knowing that the momentum of the system is going to be conserved will help us predict the speed of the colliding balls. Handy, right? Okay, let's put this information into practice. I will show you some puzzles. Use your knowledge of the conservation of momentum and elastic and inelastic collisions to get the balls into the target zones before the time runs out. In this puzzle, we have 2 target zones and 3 balls with the same mass. The black ball is completely inelastic, while the yellow ball is elastic, and they are both oncoming at maximum speed toward the white ball. Set the velocity of the white ball and hit the ball that you think will reach the target zone before the time runs out. Click on one of the 2 arrows surrounding the white ball and get a ball into the target zone before the time runs out. Press ready when you are all set and observe. Well done! Why was the elastic collision the fastest? That's right. In an elastic collision between balls of the same mass, the balls will simply exchange velocities. However, in a completely inelastic collision, both balls stick together, so their velocity after the collision will point towards the direction of total momentum before the collision, which in this case could only be away from the target zone. Fantastic! Let's go on to our next challenge. But first, let me ask you a question. Imagine a collision between 2 balls. Ball A has an initial momentum p of 2 kg/s to the right, and ball B is stationary before the collision. B has a mass of 1 kilo. After the collision, the velocity of A is 2 meters per second to the left and that of B is 3 meters per second to the right. What are the mass and initial velocity of ball A? That's right. To solve this problem, we need to remember that total momentum is the same before and after the collision. As a result, we have 2 equations and 2 unknown quantities. The product of the mass and velocity of ball A is equal to 2 kg/s. And the product of the mass and velocity of ball A after the collision, plus the product of the mass and velocity of ball B after the collision is equal to 2 kg/s. From the second equation we find that ball A has a mass of 0.5 kilos. Finally, if we substitute this value in the first equation we find that the initial speed of ball A is 4 meters per second. Ready to apply this calculation to a puzzle? Knowing that the mass of the yellow ball is 0.2 kilos, all you have to do is set the mass and initial velocity of the white ball so that A. The momentum of the system is 0.9 kg/s. B. The velocity of the yellow ball after the collision is 3 meters per second, so that it reaches the target within 1 second. C. The velocity of the white ball after the collision is 0.75 meters per second. Click on the arrow next to the white ball to set its velocity and on the Select Mass button to set its mass. Your goal is to send the yellow ball to the target zone and satisfy the 3 conditions of the puzzle. Press ready when you are all set and observe the values of the velocities and momenta of the 3 balls when the shot is taken. Raise the lab pad if you need to look at the puzzle conditions again. Brilliant! you were able to calculate the mass and initial velocity of the ball. Now, let's rock our final challenge. Here you have 3 balls and 2 possible paths. In one, you have a black ball, which is an inelastic soft clay ball, and, in the other, a purple elastic ball. The clay ball and the white ball have the same mass, while the elastic ball has a mass that is 4 times higher. Choose which ball you want to hit with the white ball to reach the target before the time runs out. Select one of the 2 arrows next to the white ball and choose the velocity in one of the 2 possible directions. Press ready when you are all set and observe the values of the velocities and momenta of the 3 balls when the shot is taken. Well done! Why was the inelastic collision the fastest? That's right. Because of the conservation of momentum, the heavier ball will never acquire enough velocity to reach the target zone on time. Now let's learn something more about completely inelastic collisions by replying to one last question. Imagine 2 balls with the same mass, one moving with a given speed and the other one standing still. After the collision, both balls are stuck and travel together. What is the speed of the joined balls after the collision? That's right. Because both balls are stuck together after the collision, they must have the same final velocity, which can be calculated using the conservation of momentum. It's incredible how much a game of pool can teach you. Now you know that total momentum is always conserved in collisions and can distinguish between elastic and inelastic collisions. I'm sure after this session Newton will surely improve his pool skills.
For sure. Now I feel ready to challenge Hook with a pool game. See you soon and thank you for teaching me some tricks.
Let me ask you one last question. Do you feel like you gained relevant knowledge during this simulation? Thank you for your feedback. Your score has been saved together with your 100% progress. Congratulations, you have completed the simulation. We hope you enjoyed it and you feel wiser now.